Hello guys, hope you're doing well. It's good to see you again. This is going to be lecture 3, the periodic table and naming out of 110. So let's go ahead and get started with that material. I am going to share my screen with you so that you can see what I see and we can talk about the same things. So these are the topics we're going to cover today. We're going to talk about the periodic table, quantum numbers, orbitals, electron configurations, periodic trends, molecules and molecular compounds, empirical formulas, ionic compounds, and naming. Notice that parts of this are from chapter 2, parts of this are from chapter 7, and parts of this from chapter 8. This is all indicated on your schedule, but those are where those things are coming from. You'll see that those textbook chapters and sections are listed here. So that's what we're going to be talking about today. Now, we always start with a review from the last time. So in order to do that, I need to pull over my paper. Sorry, just a moment. I didn't think I was going to need it today. This is what I get for not checking. So just a blank piece of paper that we can work with. And I'm going to put this back underneath. Hopefully put that paper back up in front. Get everything organized. And the next slide says review from last time. Draw me an atom of 13,9F-. I want to see the number of electrons, neutrons, and protons. So again, let's pull up our piece of paper and let's see what we can do with this. So 13,9F-. So if I look at F, F is number 9. So that tells me that I have an atom that contains 9 protons, right? So I know that I have protons and neutrons in the center of my atom, electrons floating around that. So I'm going to go ahead and put 1, 2, 3, 4, 5, 6, 7, 8, 9. I'll put pluses in all of those. They don't look very good, but that's okay. Those are my protons, and I have 9 of them in the center. Now, I need to know how many neutrons that I have in this particular molecule. Remember that we take the mass number, 13, subtract the number of protons, and that'll give me the number of neutrons that I have. And that gives me 4 neutrons in this particular species. So I'm going to draw 4 neutral particles, just randomly around that. It doesn't really matter where I put them. So it's not an accurate depiction of what this thing looks like. It's just a way for us to say that I know how many. So 4 neutrons. And then, of course, I would expect, given that this is number 9, that there would be 9 electrons. However, this has a negative charge. So instead of 9 electrons, I need to have 10 of them. Now, I'm going to draw some circles around it because that's what the pictures that we saw last time looked like. And I'm going to draw an electron there and an electron there. That's 2, 3, 4, 5, 6, 7, 8, 9, and 10. Now, I know this is not a particularly accurate picture of what this actually looks like. I get that. And if you don't understand that yet, we'll get to that. But this is one of the pictures that I've asked you to be able to draw. This is based on the Bohr model of the atom. And this shows everything that I wanted to see, i.e. the number of neutrons, the number of protons, and the number of electrons. I can specifically point out that there are 9 protons, 4 neutrons, and 10 electrons in this particular species. And that's the drawing that I was looking for, okay? So I have shown you that. Awesome. That's our review from last time. And let's take a look at what we are going to talk about now. Questions, comments, problems. Again, if you have questions, comments, or problems, please let me know. I am available via email, phone, in person, whatever, so that we can talk about whatever it is you have concerns about. Just let me know what it is you're concerned about, and we'll talk. All right. So what's next? The periodic table of the elements. Woohoo! This is a fancy looking periodic table. The one you get on the test is not quite as interesting. Some periodic tables have more information than others. We're going to use this as the one that we talk about in class. Again, the one that you have on the test has the symbol, the name of the element, the atomic weight. So that's probably all you're going to see. There's a bunch of other stuff on this one that you won't get on the test. Now, one of the questions that we get is, why is this arranged the way that it's arranged? Why does hydrogen happen here, and helium happens here, and lithium's over here, and cobalt's in here, and yada, yada, yada. And that's all based on them having similar chemistry. So if they have similar chemistry, they're going to be in a similar place in the periodic table. Now, we now know that that chemistry has a lot to do with the number of protons, neutrons, and electrons that this thing has. And that's really interesting and useful information for us, because we can use this table to help us get through all of that information. All right. One of the things that I want to talk about at this point, groups. Groups are columns containing elements that have similar properties. And that's usually because they have the same number of valence electrons. Valence electrons we haven't defined yet, but it is a number of electrons that's actually in the outermost portion of that molecule or that atom. And that's what really determines its chemistry, is those outermost electrons. Now, don't worry about that for now. We'll talk about it again. But these will have similar chemical properties based on the number of electrons that they have available to work with. Okay. We also have periods, which are the rows in the periodic table. Those periods are the number of the row determines the highest valence shell orbital. So this row number tells you how far from the nucleus that those electrons in the outer shell exist. So it's a distance measure. We also have types of materials. So you'll notice that there's this line right here, and there's a bunch of stuff over on this side of that line, the right of that line, and there's a whole bunch of stuff over on the left side of that line. This line right here we call the metalloids. So they have some properties of metals, some properties that are not metallic. So we call them metalloids. Everything to the left of that, all of this stuff in here, those are metals. Everything in this corner right here, those are the non-metals. Okay. So those are the big groups that we want to point out in looking at that. Groups that you need to be able to talk about. This one right here, which is the alkali metals. This one right here, which is the alkaline earth metals. We'll talk about the halogens, the noble gases, and the calcagens. And I'll do this again in a few minutes when we get to those particular terms. But those are things that we're going to be wanting to talk about. As we go, I'm going to show you as many correlations as I can to this periodic table. Because if you associate that information with the periodic table, and you know that you have a periodic table on the test, then it's easier for you to pull that information back out when you're taking that test. Okay? So that's my goal there. Now, I said we were going to point out a couple of things, and I did talk about this a couple of minutes ago. So the groups, those are the columns containing materials that have similar properties. So these columns have similar properties. We can then talk about the periods, so the rows that these things exist in. And again, we can talk about the row number telling us where exactly those outermost electrons live. We'll talk about that again later. We can talk about the types of elements, and we did talk about this. So the metals are most of the table. Like I said, it's everything over here and down here. The metalloids is this stair step right here, and the non-metals are up in this corner. So those are the groups that we typically talk about. So those are the things that I wanted to specifically point out at this point. Now I'm going to show you this. You need to know the following groups. So 1A, those are the alkali metals. 2A, the alkaline earth metals. 6A, the calcagens. 7A, the halogens. And 8A, the noble gases. Let me go back. So alkali metals, group 1A, is right here. So we're talking about that guy right there. So this group, those are the alkali metals. The alkaline earth metals are the second group, okay? So our second group right there. We can talk about the noble gases. That's this group right here, that very edge group. If we go one in from that, those are the halogens. So these guys right here are the halogens. Fluorine, chlorine, bromine, iodine, those guys, those are the halogens. And then the next one in is a group called the calcagens. Now, I don't understand why we need to specifically know the name of the calcagens, but apparently we do. So those are the ones that you need to know, is those 5 things. You should be able to take the names of these 5 guys and show me where those are on the periodic table without having this group thing here. So you should be able to label these things on a periodic table when you're looking at it, okay? That's my expectation. And what's the information that's on a periodic table? Well, we talked about this a little bit last time. I showed you an element and I showed you some information about what was contained there. We'll find the atomic symbol. We'll find the atomic number. We'll find, and I'll go back to the periodic table in just a second and show you all of this. Atomic symbol, atomic number, the atomic mass, the group, i.e. where it is in that periodic table, whether it's a metal or a non-metal or a metalloid, okay? So that's the information that we'll be able to get off of the periodic table. And like I said, you'll be able to get the symbol. That's always going to be shown to you. You'll be able to get the name of this thing. You'll be able to get the atomic number. This is number 1, this is number 3, this is number 4. And the mass, if you look really, really small, that number right up in the top is the mass. That's the atomic mass of that thing. All right? So, awesome. Questions, comments, problems so far? Sweet. We're now going to talk about something called quantum numbers. Now, we drew a thing that looks like a bunch of circles around the center of a nucleus. And I said that that really wasn't a good picture of what an atom looks like. That's the Bohr model. It's the one that we had initially. We know that that does not really represent what we're looking at. So what we do have are quantum numbers. There are 4 quantum numbers that exist. The N, which tells me the principal quantum number, is the energy of the outermost orbital. Okay, this is what I was talking about when I was talking about that row number on the periodic table. That N is the row number, okay? Sorry. We can talk about the L quantum number, which is called the angular momentum. It tells me what shape that orbital is, and I'll show you the shapes and talk to you about what they mean a little bit later. So L down here, you'll see that's the name of the orbital, is S, and it has an L of 0. P has an L of 1. D has an L of 2, F has an L of 3, G has an L of 4, and H has an L of 5. Those are the only ones that we talk about. Now, the values that L can have can be whole numbers up to n minus 1. So if my row is 2, then I can only have an L of 0 and 1. So it has to be n minus 1. So if I'm in the second period, then I can only talk about an S and a P being present in that area. We'll show you what that means in a few minutes. ML is the magnetic quantum number. It tells me the direction of the orbital in space. So I have some of these where their number is more than 1, right? And that means that I'm going to have multiples of them, okay? So for an S type, there's only 1, and it's spherical. For a P type, there are actually 3 of them. And there's one that goes on the x-axis, one on the x, one on the y, one on the z. So that will tell us which of those directions it is. Now these L's, MLs, can go from negative L to L, including 0. So there are 2 L plus 1 values available. All right, but that tells you which direction we're talking about. We don't really talk about at least I'm not going to talk about direction with anything beyond P. There are 5 directions for D, but they're very complicated and they're mathematical, and it's just more than I want to deal with, and probably more than you need to deal with. So MS is our spin quantum number. It indicates the direction of spin on the electron. So an electron always spins. It spins in one direction only, and that's either a negative direction or a positive direction, okay? These are conventions that we talk about. So these are the quantum numbers that we're going to be talking about. I will show you how they all apply as we go through this discussion, okay? When we talk about atomic orbitals, in my n equals 1 row, so that being this row right here, so H and HE are in row 1. So in 1, I only have one L, so it's n minus 1, which is 0. That ML also has to be negative L to L, so it's 0 as well. That means it has one orbital, okay? Its atomic orbital designation, because the n is 1, is 1. Since its L is 0, it's an S, so 1s, okay? When we go to the second row, so that second row of stuff that we have, which goes from lithium all the way over to neon, that's my principal quantum number 2. In that, I can have two different L's, one that's 0 and one that's 1. When we talk about the ML, that's always negative L to L. So for a 0L, I only have ML of 0. For an L of 1, I have an ML of negative 1, 0, and 1. Since both of these values right here are 0, that means there's only one of those orbitals. And that means it's a spherical. We talked about that before. And that means it's a 2, since the principal quantum number is 2, and an S, since it's spherical. Okay? For the L equals 1, there are 3 of them. 1, 2, 3. Since I have 3 MLs, I have to have 3 of them. We call those p orbitals. And I have a 2, because it's n, is 2. 2px, 2py, and 2pz. So there are 3 orbitals that have the exact same energy that have different locations in space. Okay, one of those being X, one of those being Y, and one of those being Z. We don't really talk too much about there being an X, a Y, and a Z. We don't really talk about them being different in that way. But we do talk about the fact that there are 3 of them. Okay, we're then going to talk about n equals 3. We have the S type that we had before, so we get a 3s. We also have a p type that we talked about before. We get a 3p. And now we have a new one called a 3d. So that's an L of 2. That's a D. Its ML values are negative 2, negative 1, 0, 1, and 2. So there are 5 directionalities for these things. There are 5 orbitals, since there are 5 directions. And these are the designations for those directions that we get. 3dxy, 3dyz, 3dxz, 3dx squared minus y squared, and 3dz2. I don't care that you know those. What you need to know is that in the D type, there are 5 orbitals available. And while they are 5 different ones, they all have the same energy. So that's what we're talking about there. All right. So far we have a 1s, there's a 2s, and there are 3 2p. There's a 3s, 3 3p, and 5 3d. Okay? So we have different types of orbitals that go with those quantum number designations. Types of orbitals. An s orbital is spherical. So a 1s is smaller than a 2s, which is smaller than a 3s. That principal quantum number tells me how far away from the nucleus that I am. So as I get bigger, I get further away. P, there are 3 of them. I have a px, a py, and a pz, and they're dumbbell shaped. I know that I can have 2 electrons in an s-type orbital and 2 electrons in each of the p's. So I get 2 in the px, 2 in the py, and 2 in the pz. So total of 2 electrons for an s-type, total of 6 electrons in p-types. For D, since we have 5 different orbitals, and this is what they look like, there are 5 of them. Each orbital can contain 2 electrons. And that means that I have a total of 10 electrons that can be present in this 3D level, okay? And remember, we talked about the spin, and I said the spin was either negative or positive. That's why I can have 2 electrons in each of these orbitals, because that means that each one of them has a different complete address, all right? So there is no case where I have the N being the same, the L being the same, the ML being the same, and the MS being the same. So I can have cases where the N is the same. So 3S, 3P, 3D, all right? Those all have an N of 3. I can have cases where I have a ML of P, so ML of 1. So that's going to be for 2P and 3P, which is not shown here, but they do exist. I can also have a case where I have multiple directions that we talk about. So some things can have, I can have multiples that are on the PY, right? I can have that. But in those, so in like this case, where they're all 2s, they're all an ML of 1, i.e. they're P's, their spin or their directionality is different, right? So these 2 have a different direction than these 2 that have a different direction than these 2. Only one of these can be up, one of these is down. So that is a different complete address for each of those things. No 2 electrons can have the same 4 quantum numbers. All right. Now we also talk about Fs. All right. There is an F that for the F, rather than being 1, 3, 5, there are going to be 7 of those. Each can contain 2 electrons. So F can have a total of 14 electrons. So that's the total number that can be present. All right. Well, I've mentioned energy a couple of times. What the hell do I mean by that? Well, what happens is as I get further away from the nucleus, I have a greater energy that's required to hold that particular electron in place. It has a higher energy. And so 1s is small, 2s being the next one in line is small, is a little bit bigger. P is a little bit higher than that because it's more complex. We then find that we go to 3s, which makes total sense. Then we go 3p, but we don't go 3d next. Even though there is a 3d, that's not the next one we fill, it's the 4s. Okay, now how the hell am I supposed to remember that? Well, there's this thing, and this can help you remember that. But there are other ways to look at that, and I'm going to show you the way that I remember that. The way that I remember that is by going back to my table. So here, this is quantum number 1. So n equals 1. This is an S-type orbital because n minus 1 is good, or the n number being 1 minus 1 is going to be 0, which means it has to be an S-type orbital. So I have a 1s. There are 2 electrons that go in it, 1 here and 1 here. And that's all I get in the 1s. Then I go to 2, and first I have an s that I need to deal with. So that's this and this. So I fill the 2s with 1 electron here and 1 electron here. I then go to 2p, which is over here. So 2p1, 2p2, 2p3, 2p4, 2p5, and 2p6. Total of 6 in those p's. Then I go to the third row. So this is 3s again, because we're filling 1 and 2. So that's an s. It's a spherical one. We then jump over here to the p, which is the next one in the orbital energies. So 3p, 1, 2, 3, 4, 5, 6. And then we go to the next row. And we come back over here. This is a 4s, because we're still in this set of groups. So we're still in the 4s. We then come to this group of 10. 10, that's a D. So that's where my D's fill is right here. And that's always going to be n minus 1 because this D, remember, is a 3D, not a 4D. And then I go back to 4P. So you may see people talking at some point about these being S over here, these being P over here, these being D over here, and these being F down here. And that is what we're talking about. That's how we know what order those fill in. We know what types they are. They're associated with those parts of the table. Okay? Now, if that is not clear to you, please talk to me and I'll see if I can show you. So, like I said, principal quantum number n equals 1. All right? That gives me an S-type orbital, which is this and this one over here in that particular row. That one's weird. And that's because this is a noble gas, even though it only has 2 electrons. It's weird for that group. This is my p group, right? So this is where I fill those p orbitals. This is where I fill the d orbitals, and rather than being n, it's n-1. And this is where I fill the f orbitals, and this is going to be n-2. So if you walk all the way through it, you'll see that that is an n-2. All right? So again, your n is the row number. Your L is determined by which type of orbital you're in, an S, a P, a D, or an F, S being 0, P being 1, D being 2, F being 3. And then you have your directionality on that, which we don't really talk about that in terms of where this is here, because since they're all the same energy, it's not important that we talk about it. Okay? We need to know that there are 1 of them, 3 of them, 5 of them, 7 of them to be able to figure out how they fill. But that's a little bit different, and we'll get to that as we go on. All right, so I hope that that helps with how we do that. Now, electron configurations. Now, electrons have spin. That means they either spin clockwise or counterclockwise. So -1/2 and 1/2. I always talk about them as up and down. All right, that's the way we talk about that. The Pauli exclusion principle states that in one orbital, you can only have 1 electron with an up spin and 1 with a down spin. So I can only have 1 of each type. I can't have 2 of the same type. I gotta have 1 of each type. Hund's rule says the electrons do not pair, have the same spin, or share, be in the same orbital unless they have to. I mean, let's think about this for a second. If you can afford it, why do you gotta have a roommate in the same room as you? Why would you do that? If you can have 2 rooms, wouldn't you do it that way? And that's the same kind of thing that we're talking about here. So unless there is no way for them not to pair, they're not going to pair. So that only applies if there is more than one of the same type of orbital. So when we talk about those P's, we're going to get 1 in the PX, 1 in the PY, 1 in the PZ. Then we'll get 2 in PX, 2 in PY, and 2 in PZ. Okay? Since the 2 electrons have a different spin, then paired electrons are not attracted to a magnet. We have both spins present. So if they're paired, if there's a 1 up and a 1 down in those orbitals, then it's not magnetic. So it's listed as diamagnetic. Those electrons that are unpaired, that are in an orbital all by themselves, those are attracted to a magnet, and we call those paramagnetic. Okay, so it's the pairing of the spins that means that it's not magnetic. Unpaired spin means that it is magnetic. In a hydrogen atom, there is only 1 electron present, and it's in that 1s orbital. So we give that electron configuration of a 1s1. So 1 being the principal quantum number, s being the type of orbital, and then 1 being the number of electrons that are present in that. Okay, so that's an electron configuration for that particular atom. All right, and if we go back to the periodic table, and I'll just show you this one, we know that H is n equals 1. It is in an S group, and there's only 1 electron in it. So it's a 1s1. That's where we see that, okay? So for atoms, when we do our electron configurations, that's easy. All we have to do is follow the table, okay? So what do I mean by that? Well, let's go back to our table and we'll talk about it. So from here, we know that this is a 1s1. Hydrogen is a 1s1. When I get to helium, that's a 1s2. So now I have 2 in that S for row 1, and that's all I have. Then when I come down to lithium, I'm going to have my 1s2, just like I did before, and a 2s1, because there's 1 electron in that S from this lithium. Now, when I go to the next one, the beryllium, I'm still going to have the 1s2. That's always going to be true. Once I've gone past it, I still have it. And then I'm going to have a 2s2, because that 2s now contains 2 electrons. Next, I'm going to go to the 2p's. And I'm going to go 2p1, 2p2, 2p3, 2p4, 2p5, and 2p6. So if I'm here at neon, its complete electron configuration is 1s2, 2s2, 2p6, because everything is full. Both the S's are full and the P is full. We then go down to group 3. And so when I'm talking about sodium, that's going to be a 1s2, 2s2, 2p6, 3s1. Magnesium is going to be a 1s2, 2s2, 2p6, 3s2, because there are 2 electrons that I get from this, all right? The next place I go is 3p. And so aluminum is a 1s2, 2s2, 2p6, 3s2, 3p1. We then go 3p2 for silicon, 3p3 for phosphorus, a 3p4 for sulfur, a 3p5 for chlorine, and a 3p6 for argon. Okay, so that's how that works. Now when we go to n equals 4, we go 1s2, 2s2, 2p6, 3s2, 3p6, always the same build, and then 4s1, then 4s2. Then I go to 3d1, 3d2, 3d3, 3d4, 3d5, 3d6, 3d7, 3d8, 3d9, and 3d10. And then I go back to 4p for 4p1, 4p2, 4p3. Now notice, that gets really, really long. And so one of the things that we do is we have a slightly shorthand notation. We can talk about the noble gas before it and say, okay, this has the same core as the argon. And then I'm adding electrons in the outermost shell, the one that we'll call the valence shell. And since the ones in the valence shell are the only ones that are actually involved in the chemistry, I just want to list what is in that valence shell and not really worry about what's in the core. So we'll list the core as argon for this. And then when we go to K, potassium, it's going to be the argon shell and then 4s1. Okay, so that's our shorthand that I'll show you in just a few minutes. But that's what we're talking about as far as following the table. That's awesome. For atoms, that's easy. Okay, but what happens if I have an ion? What happens when that happens? So I have an ion, that's a charged particle. It's either going to have gained electrons or lost them. We always take those electrons from the outermost shell. So we take them from the valence, okay, and the biggest energy shell that I have. So if we're talking about this guy right here, we take it from the 4p, okay? So we take it from there. The same trend will be true when we add electrons. They're always added to the outermost shell that is partially full, and that's the way we do it, okay? There are a few weird exceptions to do with this, and we'll talk about that, okay? So, like I said, lithium being number 3, I have a 1s2, 2s1. So my 1s is full, there's one up, one down, and 2s1, that's unpaired, so that's going to be a magnetic thing. Beryllium, on the other hand, it's going to be 1s2 right there, 2s2 right there, completely full, paired, paramagnetic. Boron, B, 1s2, 2s2, 2p1, 1s2, 2s2, 2p1. Okay, again, unpaired, going to be diamagnetic, so it is a magnetic thing. Now, when I said that we wouldn't pair unless we had to, when we talked about Hund's rule, that's what you see right here. So as I add to carbon, and I add that second electron into the p's, it doesn't pair with this one. It goes into its own place. So it goes into a different orbital because it can't. The same is going to be true when I add the third one. But when I add the fourth one, somebody has to pair. And so we're going to end up in a situation where I have one up and one down in one of them and the other two unpaired. So that's what I mean by we're not going to pair unless we have to. Okay? So that's my electron configuration for everything up to neon. So 1s2, 2s2, 2p6. Cool. I want you to practice. Practice, 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 practice. So this being asynchronous, I want you to draw the electron, or to write the electron configurations of the elements 1 through 12 right now. I'm going to pause while you do that, and then I'm going to set up my paper so that we can show you what those 12 are going to look like. Okay, so I want to do the ones 1 through 12. I'm going to pull my paper back up now that we're unpaused. Hopefully you paused and did what I said you should do. I hope you did. The other thing I'm going to do is I'm going to pull up that periodic table. So this is a slightly different one. This is just one that's available on the internet. And I will use this while I'm talking about elements 1 through 12. So element 1 is right here. I know that's a 1s1. 1 electron, 1s1. So that's number 1. Number 2 is going to be a 1s2. So again, that 1s2 occurs over here. Helium, he's over here. He's still filling in a 1 because he's in the first row. He's still filling in S even though he's over on this side. And there are now 2 electrons in that 1s. Okay, he's an exception to that rule. And that's because he acts like a noble gas. And that's why he's over where he is. Okay, when we talk about lithium, that's going to be a 1s2. And then we have 1 additional electron. So that's going to go into 2s1. When we talk about beryllium, that's going to be 1s2 and then 2s2 because I now have 4 electrons in that I have to deal with. So 2 in the 1s and 2 in the 2s. Okay, so that's beryllium. Then we talk about boron. Boron is over here in the P group. And I'm going to move over a little bit so you can hopefully see that. So this is my P group. Boron is the first one in that. So I still have that core 1s2, 2s2, and I'm now going 2p, and there's 1 electron in it. When we go to carbon, same core, 1s2, 2s2, 2p, 1 and 2 to get to 6. So that's a 2p2. Nitrogen, it's going to be a 1s2, 2s2, 2p3. And again, I can count that in my, sorry, I'm showing you on my periodic table. So I have a P1, P2, P3. Okay. Now I'm going to need a little more paper for this. So I'm going to go oxygen over here. That has a 1s2, 2s2, and a 2p4. So again, 1, 2, 3, and 4. We talk about fluorine, same core, 1s2, 2s2, 2p5, because I've added 1 additional electron. When we talk about neon, that's a 1s2, 2s2, 2p6. And that gets us to 10. Awesome, we got to 10. So now we have 2 more that we need to do. We need to do 11 and 12. So 11 is sodium. He still has a 1s2, a 2s2, a 2p6, and now a 3s, which contains 1 electron from this row. So 1 electron added in that 3s group. Okay. We then have magnesium. That's number 12. He's a 1s2, 2s2, 2p6, 3s, and now we're full in 2. So 1s1, 3s1, 3s2. So that's my complete configuration for the magnesium. Now, if you sum all of the electrons that are in this, you'll see 2 plus 2 is 4, plus 6 is 10, plus 2 is 12. So that is consistent with being number 12, which is what I was trying to do. Okay, so that's what we're trying to do when we're doing these builds. So it's always going to build based on where they are in the periodic table. First row is 1s1 and 2, 2s2 here, 2p6 over here, and again, it's not the whole thing. So 2p6 over here, 3s2, 3p6, 4s2, 3d10, if it's totally full, and then a 4p6 available there. Okay, so that's the practice that I wanted you to do for those. Whew. It's not as bad as I thought it would be. Now, I can draw this in the other way that I showed you, So with the boxes, so I have a 1s box, I have a 2s box, I have 3 2p's, I have a 3s. And since we were talking about 12 the last time, I know that my 1s was full, so that's 1 up and 1 down. My 2s was full, so that's 1 up and 1 down. My 2p, I go 1 up, 1 up, 1 up, 1 down, and then 1 down, and then 3s up and 3s down. So that's that configuration we would show if we wrote it like this. Now, occasionally you'll see this also as your 1s is here, your 2s is here, with energy going up. 3s, and then 3p. Oh, what have I done? Got myself confused. So again, this is going up. This is my energy scale. 2s, then 2p, then 3s, and then 3p this way. And again, if we were doing number 12, we'd be talking about 1 up, 1 down, 1 up, 1 down, 1 up, 1 up, 1 up, 1 down, 1 down, 1 down, 1 up, 1 down. And that's number 12. So that's magnesium again. So there are a number of different ways that we can represent this, all of which mean basically the same thing. Now, one of the things that I talked about was that shorthand notation. So if we're talking about magnesium, which is number 12, which is over here in my 3s2, the core for that is the noble gas before it. So the noble gas before it is neon, which is number 10. So I can write this as neon, as the exact same electron configuration as neon, plus 1, 2, 3 S2. 3s2. Okay, so that's the shorthand notation for that. And again, it's that core because we always have the same core built. All right, we will get into some exceptions later, but we haven't gotten to it yet. All right, so that's that one. That was fun. Questions, comments, problems so far? I hope not. Now, a condensed electron configuration, the noble gas notation. We use the noble gas closest to the element without going over the element's atomic number. We put the noble gas in brackets, then start with the electron configuration where the noble gas left off. And that's what I was just talking about, doing that neon core and then adding the 3s2 on top of it. So that's what that means. That's a condensed electron configuration or noble gas notation. Electron configurations for transition metals. We're now talking about getting into those 3Ds, right? So we've got the 3Ds. They fill after the 4s. So Ca, all right, where is my Ca again? Ca is this guy right here. So we've gone all through the 3s and 3p, and then we go to 4s, right? So that's where Ca is. That 4s is full. And that's what we should see in the drawing that we have, which we do. This is a argon 4s2. Then my next one, scandium, is going to be a 3d1 4s2. Okay, so this is still full. I put 1 in the D. My next one, titanium, is going to be an argon core 3d2 4s2. So this is still full. I add 2 to the 3d. We add 1 more electron, we keep this 4s full, and we add 1, 2, 3. But then we have chromium. And chromium, its electron configuration is argon 3d5 4s1. That's unusual because we've gone from 4s2 to 4s1 and from 3d3 to 3d5. Why does that happen? Because what happens when I get to that point, if I had this still full, I'd have a completely full 4s and a partially full 3d. It turns out that it's energetically favorable to have a half full 3D and a half full 4s, rather than having 4 electrons in the 3D and 2 in the 4s. So that's why we have this weird thing that happens right here. Now on the periodic table, those weird things are going to happen in specific places. So this group right here, that's going to be weird. Those are going to be exceptions to those rules. All right. The next one where we see that is going to be Cu, and that's right before we get to the Zn, which is at the very end where we've completely filled that 3D and 4s. Now, again, this is going to be a similar situation. So rather than having 4s completely full and 3D most of the way full, we're going to have 4s half full and 3D completely full. So again, we're going to have exceptions that occur here for this group, right before we get to where it's 4s2, 4d10, okay? So that's where our exceptions occur in those areas. So hopefully you understand why that happens. Now, we get weirdness when we go into the Fs as well. Are we really going to talk about that? Actually, no. I'm not going to. I mean, I encourage you to look at this, how we do the 5D1, 6s2, and the exceptions that come in here. But I'm not really going to talk about that in detail. It's the exact same reasoning that we just talked about. So we want to make sure that that F is half full and the S is half full when we get to those guys. Or that F is completely full and the S is half full when we get to those guys. Okay? So that's that. Questions, comments, problems at this point? I hope not, but if you do, please talk to me about it. Okay? So we go across a row in a table from left to right. What happens? Well, I'm adding both a positive in the nucleus, so I'm adding another proton, and a negative out on in the electrons. So the positive charge in the center gets larger, but the negative charge isn't really felt because I've added one in the same area, but I don't really feel the whole thing. So I have the same number of electrons are in the inside and one additional one in the outside. So the effective charge of that nucleus gets bigger as you go across. So the nucleus looks like it's a bigger charge as I go across the table than it actually is going to be. So that's effective nuclear charge. The increase is only slight, but as you go down a column, that's going to happen, and the effect vertically is much smaller than horizontally. Okay, so as you go across the table, you're going to see that the size of those atoms is going to go from sort of this size down in. It's going to squish in to be an effective nuclear charge, where I've got more positive charge being seen by the electrons. Okay. We could also talk about atomic radii. Oh, and what we're talking about right now, these things are called periodic trends. This is out of chapter 8. So these are the periodic trends. We can talk about the atomic radius. All right. So as we go down further away from the nucleus, those are going to get bigger. But as I just said, because of the effective nuclear charge, we're going to be bigger on this side than we are on this side. Okay. So that's the same thing that we were just talking about. The effective nuclear charge is higher as we go across. So its size is going to be smaller because the effective nuclear charge is higher. We can talk about ionic radii. All right. So if we have something, so lithium with 1 plus, Be with 2 plus. Since I've lost 2 electrons here and only 1 here, this one is smaller than this one. Even though they have the same total number of electrons, then we're going to see a much bigger pull in. We get weirdness over here too because things get, since the effective nuclear charge is larger, then we don't necessarily see the increase that we would expect. So that's our ionic radii, all right? It's not as predictable. We can talk about ionization energy. Now, what is an ionization energy? It's how much energy is required to be given to an atom to pull an electron off of it. So if I want to take an electron away, then I have to put in energy to break that and pull it off. Ionization energies increase as you continue to remove electrons. So if I remove 1, that's 1 energy. If I remove 2, that's much higher. It's much harder to do once I've already taken 1. So ionization energies increase as you continue to move electrons. There's a very large increase in ionization energy if I remove an electron from an inner shell. So it's fairly easy to take it from that valence shell, unless that valence shell is completely full, all right? But if there's only a few things out there, then it's fairly easy to pull it off. And it generally increases as you move from left to right in a period and from bottom to top. So it's easier up here than it is down here. And it's easier over here, okay? So how much energy is required to be given to an atom to remove an electron, okay? Now we have electron affinity. Now, electron affinity is the energy change that happens when an electron is added to an atom. For nonmetals, this would be energy that we give up. For metals, it's the energy required to add it. Okay, nonmetals want to gain additional electrons. Metals don't. So that's why we see this is good, this is bad. All right. Note that the energy being released is negative. Positive energies are required, or energies required to add. The most favorable is adding to F. The higher up and more right is the most favorable, and therefore the most negative values. Okay, so we're going to have the highest desire to pull in an electron when we go over and up. All right, it increases going down and left. All right, so the more favorable it is, the more negative it is. And so here are all of the periodic things that we can talk about. So our atomic radius is going to get bigger as we go down and bigger as we go from the right side of the table to the left side. My electron affinity is going to get higher as I go up in the table and over towards the noble gases. All right. My electronegativity is going to go up as I go up the table and up as I come over to this end. Ionization energy is going to be the same trend. It's more favorable when we come over here. My metallic character goes down as I go down and to the left, and my non-metallic character goes up as I go from left to right and up. So those are the periodic trends that you need to know. This image is one that most people, when I was a student, I memorized this image and then wrote it out on my exam pages as soon as I got my hands on it, because then I could throw it down and forget about it. Okay, so that's actually what I recommend to most people. Questions, comments, problems with our periodic trends. All right, so where are we going now? I'm going to talk about molecules and compounds. So what is a molecular substance? Molecular substance are those from nonmetals bonded to other nonmetals. So we're talking about that top right corner of the periodic table when they're bound to each other. These can be the same element as in O2, and we'll talk about which ones occur that way a little bit later, or different as in CO. So it can be the same element or different elements, but there's two things bound together. The use of the atomic symbols and subscripts is to convey the proportions of the compound. So I have oxygen, that's the symbol for oxygen, and then 2 indicating that there are 2 of them. I have C, which is the symbol for carbon, O, which is the symbol for oxygen, 1 of each, so it's CO. Now, H2 is listed as diatomic because there are 2 atoms. H2O is polyatomic, contains more than 2 atoms. Molecular formulas are those that represent exactly how many of each atom are in that formula. Okay, so something like H2O2 is a molecular formula. It indicates that there are 2 hydrogens and 2 oxygens there. Now, how do I know it's a molecular formula and not whatever we're about to talk about? This other thing that we talk about is called an empirical formula. So an empirical formula is the smallest whole number ratio of the atoms in the formula. So for something like H2O2, since there are 2 of each of them, I can say that I can divide both of those. My empirical formula is then HO. That is the empirical formula, not the molecular formula. It does not represent what the molecule looks like. It looks like the ratio of the, how many of each thing you need comparative to each other. So that's what we call an empirical formula. We will need to be able to work with what are the masses of empirical formulas, what are the percentages, all of that stuff is going to come down the pipe in a little while. So we need to make sure that we know the difference between an empirical formula and a molecular formula. So a molecular formula represents exactly what I have in a molecule. An empirical formula represents the smallest whole number ratio of the components in that. Okay? We can talk about molecular models. And the reason that I do this here, even though it's not relevant here, is because you're going to see a lot of these pictures. So I can talk about H2 as a molecular formula, H2. I can show you an H bound to another H. I can show you an H with a stick in between and another H. Okay, and then I can have one H and one H. These are all different ways of looking at the exact same thing. There are different purposes for each of them. Okay, if I only care what things are in the molecule, what the ratio, the molecular formula is, then I'll write a molecular formula. That's what these are for. If I'm concerned about how they're attached to each other, then I'll write a structural formula. This will show me exactly where these things are. So it's CH4, but this carbon has 1, 2, 3, 4 around it. I'm not looking at something with carbon and then hydrogen bound to that as well. The ball and stick model gives you a better idea of how many of each thing are there and the space that each one takes. So that's something that we can look at in terms of space. But that's not a space-filling model. Now that we know that these things have particular shapes in 3 dimensions, then we can talk about what a space-filling model looks like, and that gives us a better idea of how much actual physical space that thing occupies with its electron cloud. Okay? So those are the 4 ways that we typically talk about these things. You'll see them all if you go out on the internet to look at stuff. Make sure that you understand that they're not really that different. They're all basically talking about the same thing, and your purpose in looking at it will determine which one is the most appropriate for you to do. Questions about that? Okay, moving on. Empirical formulas. We talked about these. These are determined from experiment. It is the smallest whole number ratio of atoms in the molecule. We talked about H2O2, hydrogen peroxide, is a molecular formula describing all atoms in the molecule. This is the true formula. HO is the empirical formula. It's when we do an experimental determination on hydrogen peroxide, we'll find that the ratio of H to O is 1 to 1. Okay, so we need to know how to determine the empirical formula from a molecular formula, and we'll talk about how we get a molecular formula from an empirical formula. At this point, you should be comfortable taking a molecular formula and dividing everything out so that you have the lowest whole number ratio. Okay. And to see if you understand that, we're going to determine the empirical formulas for the following molecules. So I want you to do these on your own. Please take some time and do them on your own. And then let's talk about what this actually is. So C6H6, I have a molecular formula that indicates that I have 6 carbons, 6 hydrogens. My empirical formula for this, the lowest whole number ratio, is CH. Okay, so I have divided everything by 6, and that gives me CH. When we talk about N2O5, I can't divide 5 by 2, so this is not only the molecular formula, but also the empirical formula. All right? C4Cl4, both of those have a 4 component, so I can divide by 4, and I get CCl. That's my empirical formula for this. My molecular formula being C4Cl4. My empirical formula being CCl. Let's talk about phosphorus pentachloride, and we'll get to the naming later. I have 1P, 5 Cls. There's no way I can divide that out, so that is not only a molecular formula, but also an empirical formula. And when we talk about C6H12O6, that's a molecular formula. If I divide this whole thing by 6, I end up with CH2O. And that's my empirical formula, CH2O. So what's the relationship of the molecular formula to the empirical formula for each of these? In this case, I'd have to multiply my empirical formula by 6 to get this molecular formula. This would be a 1, this would be a 4. I'd have to multiply my empirical formula by 4 to get the molecular formula. This is a 1. And this one we divided by 6, so it's 6. So that's my how I get from empirical to molecular formula. I multiply everything by 6. All right. So that's what we see there. Here's another type of practice. Oh, look. Woohoo! So that's the ratio of molecular to empirical that we were just talking about. My molecular formula being C6H12O6. The empirical formula for this is what again? Yeah, CH2O. Now, if my empirical formula is CHO and my ratio is 3, then my molecular formula has to be C3H3O3. Okay, everything gets multiplied by 3. If my empirical formula is B5H7 and my ratio is 2, then my molecular formula is B10H14. If this is my molecular formula, C4H2O2, my empirical formula is going to be C2HO, and the ratio is going to be 2, because that's what I divided everything by. So that's going to be 2. If I have an empirical formula of CH2, and my ratio is 2, then my molecular formula is going to be C2H4. So I multiply everything by 2. If I have C4O2, and I want my empirical formula for that, I divide everything by 2, so my ratio is 2. And my empirical formula, I apologize, is C2O. C2O. Okay? So that's that. Woohoo! That was awesome. And breathe. So now we've talked about molecules. We've talked about them being bonds between non-metals. We've talked about some of the, molecular formulas versus empirical formulas. Now let's talk about ions. Now, what is an ion again? An ion is something that has a charge on it. So consider Na. Remember how we discussed it wanted to become a noble gas? Everything wants to become a noble gas. So Na, being in that first group, is going to lose electrons to become like the nearest noble gas. So Na being a number 11 is going to lose 1 electron to go back and be like number 10, which is neon, right? So how's it going to do that? We take 1 valence electron from the outer shell and give it to something else, okay? In that case, it then has a positive charge. So we've taken 1 electron away. Na plus is an ion. It is a charged particle. Ionic compounds are formed between metals and nonmetals when the atoms have become ions. Okay, so we've lost electrons on one, gained electrons on the other. We form compounds between them, and they mix in fixed ratios based on their charges. Now, positive ions are called cations. Negative ions are called anions. Okay, fine. So we know that metals want to be cations. They want to lose electrons. And nonmetals want to gain electrons to become anions. But how many will they lose or gain? And that depends, for the most part, on where they live in the periodic table. So we're going to talk through a few of these. And I'm actually going to write, I'm going to have all of these written over here. But we're going to talk about lithium, oxygen, calcium, and chlorine. And I'm going to show you a periodic table so that we can try and do this. So we want to talk about lithium. Lithium is number 3, right? So if lithium is number 3 and the nearest noble gas is helium, then I'm going to lose 1 electron to become like helium, and I'm going to be Li+. Okay. Oxygen, number 8, he's right here. I want to be like the nearest noble gas. So I have 2 options. I mean, realistically, I do. I could lose 1, 2, 3, 4, 5, 6 electrons to become like helium, or gain 2 electrons to become like neon. It is much easier to gain 2 electrons to become like neon. So O is going to be -2, and that's because it's 2 away from the noble gas. Ca, number 20, he's right here. He wants to lose electrons to become like argon, the nearest noble gas being number 18. In order to do that, he has to lose 1, 2 electrons. So he's going to be a 2+, Ca2+. And then we talk about chlorine. He's number 17. He only needs to gain 1 electron to be like argon, and so he's Cl-. Okay, so that's how we determine that. It's how many electrons do I have to lose or gain to be like the nearest noble gas. We'll talk about why we do that later, but that's how we work that at this point. Once I know what the charge is on a particular thing, so I know that calcium is 2+, if I want to match that with a Cl-, I'm going to need 2 Cl- to make a neutral molecule with that Ca2+. Okay, so that's how that's going to work. All right, practice, 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 practice. And that's what I want you to do here, is to predict the charge on the following ions. All right, I'm going to give you time so that you can do that. I want you to practice these things, and then I'm going to talk about what exactly these things are. I am not going to go back and refer to the periodic table the way that I've been doing, but I am going to expect that you can look at a periodic table and see what I'm talking about. All right. So when we do this, S is going to gain 2 electrons to become like the nearest noble gas, so it's going to be S2 minus. Strontium, being an alkaline earth metal, is going to lose 2 electrons to become Sr2 plus. K, being an alkali metal, is going to lose 1 electron to be K plus. F, being a halogen, is going to gain 1 electron to be like the nearest noble gas, so it's F minus. Calcium, we talked about this, he's an alkaline earth metal. He loses 2 electrons to be like the nearest noble gas, and so he's going to be Ca2 plus. Nitrogen is actually going to gain electrons to become like the nearest noble gas. And that means he's going to be an N3 minus. All right. He has the option to lose electrons as well, and sometimes he is positively charged, but he is fairly electronegative, and so it's easier for him to gain electrons than to lose it. I is a halogen. Nearest noble gas is 1 away, so he's going to pick up 1 electron and be I minus. Ba is an alkaline earth metal as well. It loses 2 electrons to be like the nearest noble gas and becomes Ba2 plus. Now, Cs and Se are not as obvious. We need to go and look at a periodic table to be able to do that. So Cs and Se. And I want one that's actually late. So Cs. Where is Cs? Where are you, Cs? Oh, Cs is right here. So he's in the first group. He loses 1 electron to become like xenon. So he's going to be Cs plus. Okay. Se is the other one that I wanted to talk about. That was the other one that I said that was kind of weird. So we need to find our Se. He's right here under oxygen. So he's going to gain 2 electrons to become like krypton. Okay. So those are our predictions for those guys. Woohoo! Oh, Lord. Now, what's a monoatomic ion again? Ion means it's charged. Monoatomic means one thing. We can look at that periodic table. Those the alkali metals are in group 1A. They all lose 1 electron to become like the nearest noble gas. The 2As, those alkaline earth metals, are going to lose 2 electrons to be like the nearest noble gas. Our 3A group, okay, which is over in the S group, that Al3 is all going to lose 3 electrons to become like the nearest noble gas. My 5A, we're going to lose 2 electrons to do that. My VA, we're going to lose 3 electrons for this one, but gain 3 electrons here, and that's because of the difference in electronegativity. Since this is so much higher, it's going to gain, this one's going to lose. Right? This one's still metallic, this one is not. My calcagens, we're going to gain 2 electrons. My halogens, I'm going to gain 1 electron. All right? So these are things that we typically see in monoatomic ions as those particular charges. Awesome. Monoatomic ions. If they're monoatomic, that implies they're polyatomic. We can see mercury 1 or mercurous, that's the common name. This is my systematic name. We'll get to that eventually. HD2 plus, ammonium NH4 plus. We can talk about anions. Peroxide is O2 2 minus, hydroxide OH minus, cyanide CN minus, phosphate PO4 3 minus, and I'll let you look through the rest of this. Now, these are the hydrogen carbonate, that's my systematic name. Bicarbonate is a common name, all right? So we'll talk about the difference between those eventually. Now, this is not all of the polyatomic ions. These also exist. Now, do you need to know polyatomic ions? Not so much. Some of them will be given to you on the test. Those will probably be the ones that I ask you to work with. If I expect you to work with something that's not in the list that's provided on the test, it better be given to you in the question. And if it's not, that's my problem, because you can't do it if I don't give it to you. All right. So that's the expectation there. I don't expect you to know exactly what these things look like. All right. Questions, comments, problems on that? Woohoo! We're getting through this. We're getting through this. We're getting through this. Now, we said that the D and F blocks are different than a lot of other things. It's not as easy for them to lose a bunch of electrons or gain a bunch of electrons. So they can have many different charges. All right. And it's not that easy to predict. The most common charge for them is 2+. That's resulting from the loss of both of the s electrons that they have. So that's in that valence orbital. It's the stuff that's furthest away from the nucleus. So it's easy for them to lose those two, or one of them if it's one of those weird ones that only has one in the s. So we don't always know what the charges are on that, and they can have more than one charge. So you usually have to be told what the charge is, and that's either by seeing the charge on the metal, or by the name of the compound, or from what we call inspection. And we'll get back to that in a little bit. All right. D and F metal charges again: Fe2+, Fe3+, Cu2+, Zn+. The first one is going to be iron 3 oxide. We have a zinc 1 chloride. That's a Zn+. This is an iron, an Fe3+. Copper 2 oxide is Cu2+. When we talk about inspection, we're talking about something like this. So this is also iron 3 oxide. How do I know this is iron 3 oxide? Well, oxygen has a -2 charge, right? We know that from the periodic table. So if oxygen is a -2 charge and there's a 2 here, that means that I needed 2 Fe's to even out that 2 charge. But the Fe has its own charge, and the oxygen has to get on board with that. So in order to take care of its charge, I needed 3 of them. So that means that this is an iron 3. Okay. ZnCl, I know that Cl is 1-. That means that Zn is 1+. CuO, I know that oxygen is 2-. That means that this is a Cu2+. And on CrO4-, I know that oxygen is 2. There are 4 of them. That gives me a total of 8 negative. There is 1 additional electron there. So that's 9. That means that's Cr9. Okay? That's what his charge is in that particular state. Okay? So that's how we find all of those things. Awesome. Questions, comments, problems on that? Oh, I did that wrong. Darn it, I knew I did that wrong. So this, no? Yeah. So the 2 times 4, that gives me -8. I need 1 left. So this has to be +7, not +9. I apologize. It's +7. So that's how we do that. Awesome. Now, organic materials. Most of the stuff so far has been inorganic. It does not contain carbon. That's what organic means. So I don't care what these people tell you about how things are grown organically. If it contains carbon, it is organic. Anything you eat contains carbon, so it's all organic. There is no way for it not to be organic. And you'll hear me spouting off about this occasionally, but anything that contains carbon is an organic molecule. All right. Anything that doesn't contain carbon is said to be inorganic. All right. Hydrocarbons contain only hydrogen and carbon. Hydrogen and carbon. Alkanes are linear chains of hydrocarbons. When one or more hydrogens are replaced on an alkane, they are replaced by functional groups. These groups determine many of the properties of the molecule, and the formulas can be written for organic materials in many, many ways. You'll see that as we move on. The way that we write it will probably depends on what it is we're trying to focus on in looking at that molecule. All right. So that's your deal with organic materials. When we talk about inorganic materials, ionic compounds, we know that these things are going to make ions, right? So our metals are going to lose electrons and they're going to become cations, or nonmetals are going to gain electrons to become anions. What does that mean? Well, once they have that charge, I'm not going to find a positive charge sitting around by itself over here. Woo-hoo-hoo, hi, positive charge. Not going to happen. In nature, that positive charge is going to be attracted to a negative charge. Okay, so even though we've transferred that electron, they're still attracted to each other. and they need to be net neutral, right? So in order for that to happen, we need to make sure that we've got the same number of positives as we have negatives. So that means if this is a 2 plus and this is a 1 minus, I'm going to need 2 of these to make that work. So we do something called cross multiplication of the charges to get the ionic formula. So since Ca2 plus, I go 2 down there, Cl negative, I get a 1 there. All right, and that's right, that's net neutral, that's how that works. When we name ionic compounds, we give the name of the cation, so the positive charge is the metal, followed by the name of the anion, okay, so the negative charge, the non-metal. We change the name of the anion to be IDE, so if it's chlorine, it goes to chloride. If it's oxygen, it goes to oxide. We indicate the charge on the cation in parentheses and Roman numerals if required. So if I can have more than one charge, then I need to indicate that. All right, that's how we do that. So Fe is going to be Fe3 if iron is 3 plus, and Fe2 if iron is 2 plus. Now, common names can be used. They are sometimes used, and they're fairly common. Water is a common name for dihydrogen monoxide. So there are some of these things that are ubiquitous in our language and discussion, and so they may come up. There should be a table on the test that gives you common names versus systematic names. If you're naming something, it's recommended that you use a systematic name. You can give it a common name if you want to do that, that's fine, but it is not what we recommend, okay? So let's practice naming ionic compounds. So we're going to name a bunch of stuff, and then I want to talk about the formula of these. Again, I want you to pause, and I want you to figure out if you can do this on your own, because this is the kind of thing you're going to have to do on a test. So you're going to get these formulas, and I'm going to say which of these is, what is the name of this? Which of these is the name of that? You're going to need to be able to do it. Okay, and we're going to go the other direction and say this name needs to give me this formula. All right, that's the more common way to do it. It's the one you're going to need the most when you get to the second half of this class if you take it. So you need to make sure that you can go both directions. Okay, I will give you time to pause and do those things. And now that we've come back, hopefully you did pause. This Rb2O, well, Rb is rubidium. There are 2 of them. That indicates that since oxygen is 2 minus, that means that this needs to be an Rb plus, and the name that I would give this is rubidium oxide. Okay, there's only one way that these can come together, so it's rubidium oxide. This is calcium, this is bromine. We changed that to bromide, so it's calcium bromide. This is magnesium. This is sulfide, because we put it at the end, so sulfur becomes sulfide, so it's magnesium sulfide. This is sodium. This is phosphate. Since this is a 3 minus and this is a +1, the only way they can come together is Na3PO4, and so we call that sodium phosphate. Okay, ZnO is zinc oxide. Now, I know from looking at that since O is 2 minus, this Cn has to be a 2 plus, but it's still zinc oxide. All right, what's the formula for the following? Well, tellurium 4 chloride. So it's a +4. Tellurium is Te. Chlorine is, chloride is Cl. That's a minus. So I'm going to have TeCl4. Okay, TeCl4. And I'm going to pull out my paper just so I can show you these again. Because while I know what I'm doing, you guys may actually not know what I'm doing. So drawings that I had before, we'll have our periodic table over here just in case I need him. All right, so Te4, tellurium 4 chloride. So tellurium IV chloride, and this is of course in parentheses. So tellurium is Te. I know this is a 4 plus. Chloride is Cl. I know it's a 1 minus. And so that's going to be TeCl4. Okay. Again, with the rubidium oxide, calcium bromide, magnesium sulfide, sodium phosphate, and zinc oxide, we didn't have any weirdness in naming those. Okay. I didn't give you any weirdness that you had to worry about. All right. Here, manganese 2 phosphate. Manganese 2 phosphate. So manganese is Mn. I know that it's a 2 plus. Phosphate is PO4 3 minus. I have to cross multiply, so it's going to be Mn3. Oh, that's not the right place. Woohoo! So it's Mn3 PO4 2. So I had to get the 2 down here and the 3 down there. So it's Mn3 PO4 2. All right, that's that. Let's go ahead and move over and we'll talk about Zinc One Nitrate. So zinc is Zn. I know he's a +1 because the charge is there. Nitrate is NO3 minus. You can look at that in the list of polyatomic ions. And since this is plus, this is minus, I then get ZnNO3. These parentheses are not required, but you can include them. That is entirely up to you. So aluminum oxide. So aluminum is Al. Oxide is O. This is 2 minus. Aluminum is actually 3 plus. It's most common. So then I have to cross multiply. So I get Al2O3. Okay, that's aluminum oxide. And then calcium bromide. So calcium is Ca. I know that since it's an alkaline earth metal, it's going to become a 2 plus ion. Bromine is Br. He's going to gain 1 electron to become Br minus. Cross multiply, I get a CaBr2 to make that net neutral. Okay? So that's how we work with all of those happy things. Hopefully you don't have any questions about that, but if you do, please let me know. All right, let's move on. Woohoo! Questions! Yay! All right, so we talked about ionic compounds and how we name them. Now we need to talk about how do we name molecular compounds. We talked about what they were. We talked about their empirical formulas versus their molecular formulas, but I haven't talked about how to name them yet. So let's talk about that because it is very different than what we did with the ionic compounds. So systematic names are those you need to know. Common names may be referenced. Some need to be known. They will be in a table on the test. You can look at that before the test, and I will post those tomorrow, I promise. Binary compounds are named by naming the atom that comes first in the formula, and then name the second item and change the ending to I. So that's very similar to what we had before. For example, let's name NO. N is nitrogen, O is oxygen, so it's nitrogen oxide. Awesomeness. I can do that. Woohoo, that's easy. But we know that this can be NO or N2O, right? It can be N2O, it can be N2O4, it can be all kinds of different things. So how do we tell them apart if they both have nitrogen and oxygen? Holy crap, we can't. So we attach prefixes to the names to indicate how many there are. Unlike ionic compounds, which have a fixed ratio in which they're going to hang out to make sure that they're satisfied electrically, these could hang out in many, many different ways. And so we need to make sure that we say how many of each there are. So if the item is only one, the mono can be omitted for the first element. It can be done. It's not always done. So in this case, we have nitrogen monoxide. There's 1 oxygen, so it's monoxide. We don't need to list it as a mononitrogen monoxide, but we can. N2O4 is then dinitrogen monoxide. And a list of prefixes is given in the table, right? So you're going to get a table of those prefixes in terms of what they are. And that's here. So prefix, mono is 1, di is 2, tri is 3, tetra is 4, penta is 5, hexa is 6, hepta is 7, octa is 8, nona is 9, and deca is 10. Those are the ones that you need to be able to use, right? So we got through the prefixes. Let's talk about naming binary molecular compounds. Non-metal to non-metal bonds can be configured in a number of combinations to make sure that we are clear on which one way it is we use prefix for each element to know how many there are. Dihydrogen monoxide is H2O, or water. Dinitrogen tetroxide is N2O4. Like I said, these are the prefixes that you need to know and be able to work with. Occasionally we'll get something bigger than 10. That's something that you should be given if you need it, okay? We can talk about compounds containing hydrogen. They're often non-conforming to the normal nomenclature rules. So B2H6 is diborane. CH4 is methane. SiH4 is silane. NH3 is ammonia. PH3 is phosphine. H2O is water. H2S is hydrogen sulfide. Note that even the order of writing elements in these formulas for hydrogen compounds is irregular. Sometimes hydrogen's first, sometimes it's last. And that all depends on what we're doing, okay? So there are lots of weird things that can happen, and we need to be able to deal with how that works. Now, I like flowcharts. So here's a flowchart. And I took this and stole it from a place I used to work. So what kind of compound is it? Is it ionic? Then it's composed of cations, metals or polyatomic ions, and anions, nonmetals or polyatomic ions. If it's type 1, then only one type of cation is observed, and then we name it based on the name of the cation, then the name of the anion with the IDE. Type 2, more than one type of cation is possible. Then we need the Roman numerals to indicate what the charge is on our cation. Non-covalent or covalent compounds, these are non-ionic, not composed of cations and anions. They're typically only nonmetals present. Type 3, covalent, non-ionic, there are rules for that, okay? And that's what we've been talking about with denoting how many there are using those prefixes, di, mono, tetra, penta, that kind of thing. There are also acids. These are things that produce H+ in water. We'll talk about that in way more detail later. Typically, the hydrogen cation is written first in the formula. The anion doesn't contain oxygen. It has rules for that. If it does contain oxygen, there are rules for that. Okay, so this is a table of how I like to think about, okay, I need to name this. Is it ionic? Is it molecular? Is it an acid? And then there are rules that I know for each of those things. Okay, so that helps me. If it doesn't help you, ignore it. And I hope it doesn't confuse you. So what do we need to know about naming? We will consider the following cases. Ionic compounds, main group metal to non-metal or polyatomic. Name the metal and then the non-metal. Transition metals to non-metal / polyatomic. Name the metal, followed by its charge in parentheses, then name the non-metal. Molecular compounds, non-metal to non-metal. We name the atoms in the order that they're presented, whether we think that makes sense or not, and then indicate the number of each that are present using the prefixes, okay? So that's the rules for what you need to know. You need to be able to name these things, and you need to be able to write their formulas, okay? Questions, comments, problems on that? Awesome possum. We're almost done, I swear. So let's do a little practice. I'm going to give you some time. I want you to do this practice. We're going to talk about what these things are and what they look like. OBKB, let me pull up my paperwork so that I can show you what it is that these things look like. So I'm still on the same piece of paper. We're talking about CS. CS. Awesome. Carbon sulfide. Carbon sulfide. Now, that's a non-metal to non-metal. There's only one of each, so I don't need to worry about the prefixes. So it's carbon sulfide. Awesome. Now, PCl5. PCl5. We're going to start with the same nomenclature here. We name the thing that's written first, phosphorus. And then we have chloride, but I have 5 of them. So that's pentachloride. That's 5. Okay, it's the penta. Oh, awesome. CO2 is carbon. Oxygen is oxide. There are 2 of them, so it's dioxide. Sweetness. N2O4 is nitrogen, but it's not a single nitrogen, so it's dinitrogen oxide. But is it just oxide? No, because I can't leave off the mono for the second component. So it's dinitrogen monoxide. And I hope you can read that. Sorry. I'm going to go ahead and go so that I have a little more space. CCl4 is going to be carbon. It's going to be chloride. But there are 4 of them, so it's tetrafluoride. And then SeBr2. Se is selenium. And again, I can read that from the periodic table that I'm given on the test. So Se is selenium. Br is bromine. I changed it to bromide. But there's 2 of them. So it's dibromide. Okay? So, and again, that's a nonmetal to nonmetal, so I have to list how many of each there is. Okay? So now we're going to write the formulas for aluminum oxide. Formula for aluminum oxide. Aluminum is Al. Oxygen is O. This is 2 minus. This is 3 plus. So that's going to be an Al2O3. Calcium phosphate is going to be Ca2 plus. Phosphate is PO4 3 minus. And so that's going to be a Ca3PO4 2. Magnesium oxalate. Magnesium oxalate. Well, magnesium is Mg. Oxalate is one of these weird ones that I'll see in the table. It's C2O4, and that's a 2 minus. Since this is a 2 plus, then it's going to be MgC2O4. Okay? And this can be in parentheses or not. It's entirely up to you. And silver dichromate. Silver dichromate. Silver is Ag. It's typically 1 plus. Dichromate is Cr2O7 2 minus. So this is going to be Ag2 Cr2O7. Okay? Awesome possum. Sweetness. We got through that too. Whew. I can breathe a little better now. Awesome. So let's talk about what's next. Questions. That's the big thing. Now, one more thing we need to start is naming acids. When we talk about acids, we're going to define them as substances that give up H plus in water for now. In that case, formulas for acids contain 1 or more hydrogen atoms and an ion. Names are as follows. So HF is hydrogen fluoride. It's also an acid, so hydrofluoric acid. And the anion is F minus, which is fluoride. HCl, the molecular compound, is hydrogen chloride. HCl is hydrochloric acid. And Cl minus is the anion, which is chloride. Okay? If they're in this particular table, I want you to know what those names are. If I say hydrobromic acid, you should know that that's HBr. You should know that the ion is Br minus. Okay? These ones I expect you to know. Some reference acids, some other things that we talk about. We talk about carbonic, chloric. These are all acids containing hydrogen, oxygen, and something else. All right? These are reference acids. These are fairly common ones. Carbonic, chloric, nitric, phosphoric, and sulfuric. All right, again, I think you should be familiar enough to write most of these, and you will be eventually. Oxoanions are what happens when we take hydrogen off of these. So this is my phosphoric acid. Once I take one proton off, that's dihydrogen phosphate. When we take two protons off of that, that's hydrogen phosphate. And when I take all three protons off of that, that's phosphate. Okay, so this is naming what's left once we've taken off some of those protons. All right. We can talk about this. This is how we get these weird names that you see from time to time. It's a per-ic acid, reference the ic acid, an os acid. I can't remember this. And these are the other names. So I don't expect you to know how to do this, but I expect you to understand what the relationship is if we're talking about these things. Bases, for now, are defined as compounds that yield OH minus in solution. So NaOH, KOH, BaOH2 give me OH when they dissolve. So NaOH becomes Na plus and OH minus, KOH becomes K plus and OH minus, BaOH2 becomes Ba and 2OH minus. Ammonia is also a base. When I add ammonia to water, what happens is that the water or the ammonia picks up a proton from the water. So it's picked up an H plus. This donated the H plus. So this is my acid. This is my base. I end up then with OH minus and NH4 plus. And this presence of OH minus, yielding OH minus in solution, is how it's defined as a base. Okay? So that's that. Awesome possum. Next, what are we talking about next? Hydrates. Compounds that contain a specific number of water molecules associated with them are called hydrates. So if it has water on it, it's hydrated. Okay. Since the water can be drawn off by heating, the material is called anhydrous once the water is removed. All right. So you may have heard the term hydrates or anhydrous. So BaCl2.2H2O is barium chloride dihydrate. LiCl plus with an H2O is lithium chloride monohydrate. So the same rules apply to how many hydrates there are. We're going to name the compound first, and that's always based in the same rules that we have for ionic compounds, and then the number of waters that are on it. Okay, you should know what those terms mean. If I give you one of these, you should be able to give me this. And if I give you this, you should be able to give me one of these. Okay? Awesome. Almost there. I swear. We're almost there. I told you that there would be a table that had formulas, common names, and systematic names. So H2O is also known as water and dihydrogen monoxide. So this will be present for you on the test. Why is this going to be present? Because I tend to throw these terms around interchangeably without really thinking about it. So you need to know that some of these things are here. This will be present for you. It is expected that if you need that information, you'll know where it is, and you can use that. All right? Questions, comments, problems on any of the things that we've talked about. So those are my expectations. Now, I will give you practice in terms of nomenclature to give you some idea what it is that I'm looking for. Those practice sheets may have gone up already. I can't remember if they have or not. But they will go up very, very soon. I have them ready. I just need to get them loaded. Okay? So that's some of the practice that you should be able to do for that. I expect you to be good at a lot of these things. And this will be a big part of what we do on the first test. Questions, comments, problems? I hope not. And that was the longest lecture in the universe. But that was periodic table and naming. So I'm sorry that you had to sit through all of that at once. I hope that you guys are not dying and are okay out there. I'm going to stop sharing now, and I will see you next time. Hope you have fun.